John's tour of the Lost City that we all just went on, there is a, that's interesting. All right, what just happened? That's very bizarre. Here we are. So there was, let's see, Alain Leger pointed out a missing negative sign over here. So this slide has the correct equation from Lecture 4 for radioactive decay. A little bit of PowerPoint typeface problems here. But this was the equation that governed the ratio of strontium-87 to strontium-86 at present to the ratio at the beginning. 86 strontium is assumed to be constant, so the subscript actually isn't really relevant there for the stable isotope. And then minus the 87, 86 strontium. So there are a couple of negative signs there that should be in there. So if you took notes on Lecture 4, just be sure you have those in your notes. But the slides will be correct. I'm thinking of actually putting the slides on another website. I know the films will be available, but sometimes it's hard to use the material in a film because you have to watch the speaker, and in some cases that can be a real torture to have to watch that again. So at least in my case then, to spare you that torture, I'll put them on another website and give you the URL tomorrow.
But if all three speakers agree, we could put the slides on the same place as the...
Oh, that would be even better.
We can collect them on... I'm fine with that.
Yeah, that would be good.
Try to do that today.
Okay, cool. Good. Okay, so I feel now one of the interesting positive comments that I heard a lot from those attending the school was that the three speakers were converging very nicely in their particular areas, and I feel now that kind of like whales in the ocean at night, we've kind of come together, met, and now we're moving in different directions. And in fact, I'm moving back out into interstellar space while John is down in the depths of the oceans and Jim is moving through time with the planets. So I am going to spend the rest of my time on extrasolar planets. I'll return a little bit to the Earth and Titan and talking about what signatures we might look for habitable planets. But today, pretty much for me, which are my last two lectures, we're going to be beyond the solar system. So I'm going to start by talking about extrasolar planets, detection methods, and in particular, a strategy, some of the things that I think are needed, some of the unfortunate lacunas that have been created by other strategies in what we need to be able to have a good chance of detecting and characterizing a habitable planet. Now, how many people here actually work on extrasolar planet detection? Yeah, so let's go do the coffee break now, and when we come back, we'll have Jim Casting's presentation. So here we go, carrying coals to Newcastle again. So there are a number of different techniques, obviously. I've listed them here. I'm not going to give a didactic lecture about how each of these techniques work. Those of you who don't do extrasolar planets, you saw whose hands were raised, and you can go talk to them about how it all works. But the remarkable thing about this list of techniques is that with the exception at the moment of astrometry, and this is something of a puzzle, they all actually work, and they've all detected planets. In fact, the kinds of information that have been gathered from these techniques is deeper and broader than anyone could have predicted in the mid-1990s. The radial velocity, astrometry, and microlensing techniques measure the mass of the planet. The radial velocity and the astrometry techniques depend on the fact that a planet and its star orbit around a common center of mass. The planet doesn't orbit around the star. The two of them orbit around the common center. Therefore, the star executes a small orbit in phase with the motion of the planet. And that motion of the star, depending upon the orientation of the orbit in the sky relative to you, the observer, can include the full component of radial motion associated with the orbit. That's if the plane of the orbit is aligned with you, the observer. If we have the unhappy situation where you're looking at the plane of that planet's orbit face on, and the star is executing motions in the plane of the sky, then there's no radial motion. So the goal of radial velocity is to detect that radial motion with very high precision spectroscopy. And this technique has been the most successful technique in terms of detecting planets to date, although depending on the fraction of Kepler candidates that are actually validated as planets, the transit technique might end up as number one in a few years. But radial velocity was the first planet detected around a main sequence star and the most successful. The important point that I want to make is, bear this in mind of course, because you're looking at the radial component of the motion of the star, what's actually detected is the mass of the planet times the sine of the orbit inclination. So strictly speaking, the mass that's derived is a lower limit to the mass. Now, if these orbits are oriented randomly around the sky, which they should be, and you have detected a large number of planets, which the radial velocity observers have, then one can say with some confidence that something like 90% of the planets that have been detected have physical masses that are within a factor of 2 of the Doppler detected mass, the m sine I. And of course the radial velocity is detected by the Doppler shift. I didn't say that, I should have. There are many interesting effects associated with this, but I'm not going to talk about them. There are ample reviews. One book I would like to advertise, which I think is very, very well done, and I'm advertising it because I'm not an author, or in spite of the fact that I'm not an author, is a book called Exoplanets. It was just published by the University of Arizona Press and LPI. It's edited by Sarah Seeger, and it's up to date, and the chapters are well written, and it's reasonably comprehensive, but it's not an enormous tome. So you can actually read these chapters, the bulk of them, in a relatively short period of time and get a good up-to-date tutorial on this field. Okay, that's the one advertisement. Astrometry also detects the barycentric wobble. In this case, it's detecting not the radial velocity, it's detecting the change in position of the star against the sky as it executes its small orbit around the common center of mass. Because of that, the astrometric technique is not sensitive to the plane, to the orientation of the plane of the planet's orbit around that star with respect to you, the observer. You see the full component of the motion. And so with astrometry, you detect the mass, the physical mass. Microlensing is a subfield of the general field of lensing. Lensing, of course, is the phenomenon associated with the bending of light by objects that have mass, by the gravitational force associated with objects. Gravitational lensing is well known in cosmology. There are beautiful pictures, which I think all of you have seen. One of the books back there on lensing has a very amusing simulation of the Matterhorn, I guess, being lensed. That's kind of very, very nice. And microlensing is the case in which the lens itself is not resolved by you, the observer, but instead you see a change in the brightness of a background star as a lensing star passes in front of it in the foreground, sufficiently well aligned that some of the light of the background star is distorted. And then if there is a planet around the lensing star, that planet acts as a kind of a defect in the lens, and there's a secondary signal, or sometimes several secondary signals, depending on the orientation and the position of the planet around the star, and that can be detected. And that has been, it's a technique that requires a lot of observing time, because while stellar lensing phenomena can occur over periods of weeks or months, the planetary component is relatively short. It can be days or hours. So once a stellar lensing event begins, you have to have a network of observers available to continue to observe this, to catch the smaller blip in the light curve, and you don't know when that's going to occur, of course, if ever. Now, in terms of detecting the size of a planet, there are two techniques: transits and direct detection. Transit is the detection of the passage of the planet in front of its parent star, and also the passage of the planet behind its parent star. This requires, of course, that the planet be well aligned, its orbit essentially not be tilted, again, relative to you, the observer, that the plane of the orbit be essentially parallel to the line of sight to the observer within a couple of degrees. So the fraction of stars that transit is small, just as the fraction of stars that microlens is very, very small. But actually, transits have turned out to be a rather successful technique, because that fraction is not all that small for planets that are in very close orbits around their parent stars. So for close-in planets, something like 1 out of 100 for randomly distributed orbits in the sky will produce a transit. And so this technique, if you observe lots of stars from space, as Corot and Kepler have done, can yield a lot of data. And then the direct detection relies, of course, on being able to block the light of the parent star by coronagraphy or by interferometry, in which case you null the light and try to bring out the much fainter light of the planet. And this has worked for planets that are, at least up to this point, large and self-luminous. So here's a plot I showed from the second lecture on the first day. It's mass versus semi-major axis, mass in Jupiter masses. Here's a Jupiter mass, semi-major axis in astronomical units. Here is 1 astronomical unit. And the various techniques are shown, including one that I didn't mention, which is pulsar timing, where there's a change in the timing of the neutron star pulsar effect due to the presence of planets. There are 4 planets detected that way. The different techniques are color-coded, and by looking at a graph like this, you get a pretty good idea of what the limitations and the advantages are of these different techniques. They have progressed enough now that you're really beginning to see how the completeness function for these different techniques shows up on a graph of mass and semi-major axis. For example, again, the probability of a transit is much higher for a planet that's very close to its parent star than it is for a planet that's far away. And so the bulk of the transiting planets are found very close to their parent stars. And although this is an old chart, this still holds for Kepler. We'll talk about that toward the end. The radial velocity technique is relatively agnostic to semi-major axis, but not completely. There is a weak decline in sensitivity here associated with the length of time that is available to make these observations. And then, of course, there's a pretty hard cutoff here. Astrometry, there are no detections as of yet that have been confirmed. There have been some false alarms. Microlensing is an interesting case because the geometry of the microlensing experiment that is done is to look toward the bulge of our galaxy, where the bulk of the source stars are located, 8,000, 9,000 parsecs away. So the lens stars tend to be distributed between 1,000 and, let's say, 7,000 parsecs, but the bulk of them are not so close to us. And so within a factor of 2 or 3, the spacing between the lens star and the source star and the observer is about the same. And so the geometric construction of needing to have a planet in or near what's called the Einstein radius actually translates to a relatively common physical sensitivity, that microlensing tends to discover planets that are in the 1 to, let's say, 10 astronomical unit range from their parent star. And in fact, what you see is exactly that with these microlensing discoveries as of 2009, between 1 and about 10 astronomical units. You can actually detect planets that are farther out, but the sensitivity goes down. And then direct detection really does not, as of this point, do a very good job on what we would call true planets, unless those planets are very, very widely separated from their parent star. Direct detection really is a technique that up till now is looking at brown dwarfs, objects that are more than 10 or so times the mass of Jupiter. And here are our own planets. The inner solar system here looking rather lonely on a graph like this, but hopefully with Kepler and future techniques, this area will fill in, and the Kepler candidates are already beginning to fill that in. And then the giant planets, Jupiter and Saturn, are now becoming representative of objects that can be detected, and that is happening today. And Uranus and Neptune, way out at 19 and 30 astronomical units, are still very difficult targets. So in terms of sensitivity, this is an interesting chart. There are several charts to look at. This is one by David Bennett. So this is mass in Earth masses versus semi-major axis in astronomical units. What you see here is, so this is 1 astronomical unit and 1 Earth mass. Jupiter is just about here at 300 Earth masses. There are several thresholds here. These are the planets that were discovered at the time that Dave revised this chart a couple of years ago. Here's the Doppler spectroscopic or radial velocity technique. The sensitivity limit has a positive slope to it, but it's got 2 positive slopes. One here, which is simply associated with the fact that the farther away a planet is from its parent star, the longer its period is, and so the longer is the stellar period, and so the smaller is the radial velocity. And so the sensitivity goes down because for a given mass planet, the radial component of the velocity and the total velocity is simply lower for that star. So that's this gentle rise here, but then you get to a kind of an observer's cutoff here where you get to periods that become longer than the time that's available to do the observations, or if you're conservative and you need to look at 2 or 3 periods, you would have that ratio. But the point is that the farther out in semi-major axis space you go, the longer you have to look to get results. Now, astrometry is the opposite of Doppler in the sense that you're not looking at the velocity, you're looking instead simply at the change in position of the star as it's moving around the common star-planet center of mass. You don't care how long it takes if you live forever. You're just looking at the change in position in the sky. And so if a planet is farther away from the star, the moment arm of the orbits are larger. And so in fact, astrometry becomes more sensitive for planets that are in larger semi-major axes. The threshold mass that can be detected actually goes down with increasing distance until you get to a point at which the amount of observing time that is available has not been enough to capture an orbit. We'll just use that as a fiducial point. And then you get you're essentially at a wall. But if you now consider that, okay, I can look at a fraction of an orbit, it's not quite a vertical cutoff. It might be just a very steep rise in the sensitivity limit, depending on how you do your analysis of looking at partial orbits. And this particular astrometry sensitivity was a notional one for the Space Interferometry mission. Transits, again, because of the alignment issue, tend to be really best at picking up planets at small semi-major axes. This is the space for Kepler, and notice that for Kepler, this is an Earth masses, so this is not. It's very difficult to actually put a transit sensitivity on a plot like this because it's really sizes that you're looking at. But the main point is that Kepler can see an Earth-sized planet out to maybe just barely about an AU. The issue is that there's a certain fraction of stars it can look at. The probability of getting at least one transit drops precipitously as a function of semi-major axis. So for that particular sample of stars, you eventually get to the point where even if every star had a planet orbiting around it at that semi-major axis, the probability of a transit would get to less than 1 for the entire cohort. So that's kind of what this cutoff is here. And then microlensing, ground-based microlensing, microlensing Planet Finder, which is a space-based mission. The sweet spot here basically has to do with the Einstein radius and the maximal probability of getting a microlensing event at a given distance from the Earth and Sun. The astounding thing about microlensing, if in fact these calculations are right, is that it has the capability of detecting that's not the right graph. It has the capability of detecting a Mars-sized body acting as a part of a microlens anywhere between 0.8 or 0.7 and 10 astronomical units around its parent star. That is, if microlensing works from a statistical point of view, this is the most complete way to do a sample to determine the occurrence of Earth-sized, Earth mass, and even Mars mass planets in the traditional habitable zone. Now, you won't study these objects, and there are a lot of things you have to do, like be able to get the stellar mass and so on in some way in order to get the absolute planet mass. But in principle, this is the most sensitive technique. Yes?
What stellar mass was assumed for this plot? Because the semi-major axis is not relevant only for the period, but also the mass of the star, and also for the top light, the ratio is relevant.
Yeah, I'm going to get to that actually later. I think these are supposed to be solar mass stars in this case, but I'll get to the issue of the different stellar masses right now, in fact. So this is a similar type of plot that was done by the SIM people. And what's shown here is, again, planet mass sensitivity versus orbit period. Ignore all the green lines because that's a theoretical simulation. The detected planets as of 2009 are shown here. The radial velocity sensitivity curve for 1 meter per second is shown in olive here. And the advertised SIM sensitivity, which is a space-based astrometric experiment, over 5 years, is shown here for a cohort of about 100 stars. For the farthest star in the sample, you have the least sensitivity. For the closest star in the sample, and then for the median stars in the sample. And this is a sample of F, G, and K-type stars. Now, if you superimpose the kind of habitable zone calculation that Casting and colleagues did, where you have habitable zones for F2, G2, K2, and M2 stars, you can see where the sensitivities fall in terms of being able to capture an Earth, which is over here around these various types of stars. This, unfortunately, is not in semi-major axes. It's an orbit period, so you have to convert that. This is 1 year, so this is 1 AU. So Venus, which is 2/3 of a year, is about here. And of course, this is Saturn out here. And I guess, yeah, there's Venus right there. So these are advertised sensitivities. And again, this is a space-based mission that's based on a technique that from the ground has had great difficulty. This is a mission that is in preparation, Gaia, which has a lower sensitivity, but will probably actually happen. So these are the sensitivities. Now, there's another aspect to all of this, which has to do with direct detection. If we want to move from being able to know the existence of planets and their basic properties to then be able to study their spectra, there's another factor that one has to fold in, which is the fact that stars generally have dust around them, particularly if they have planetary systems. And so this is a simulation, and I drew a blank on the author's name, but I will look it up again. Somebody I know really well, and it's very embarrassing. But anyway, he did a simulation of a nulling interferometry experiment from space.
Is that Kuchner?
Thank you. It's Mark Kuchner. Very good. Mark Kuchner. There you go. Thank you. So this is a solar system at 10 parsecs as seen by TPFC, which would be a direct detection coronagraphic mission where you suppress the light of the star with a coronagraph. So here's the geometry, the star, the Earth over here. And if you have an amount of zodiacal dust that is equivalent to what we have in our own solar system, the resulting image would look something like this, where you would have the zodiacal dust showing up, but the Earth would still show up through that zodiacal dust. If you had a factor of 20 more scattering from the dust, the Earth would disappear. So the direct detection experiments are difficult to plot as sensitivities on the graphs that I just showed a moment ago. But the real key issue for those experiments are two things. One is the frequency of occurrence of Earth-like planets, which translates into what is the closest star to the Sun that you might expect to have an Earth that you can study directly. If every star had an Earth-like planet around it, you could look at Alpha Centauri, which is only a parsec away. If only 1 out of 100 stars had an Earth-like planet at 1 AU, your closest star might be more than 10 parsecs away, might be dozens of parsecs away, and that would be a problem. And then there's the zodiacal dust loading, which is something that we really don't know for any of these systems. So all of these techniques, with the exception of astrometry at the moment, are going great guns. And I'm painfully aware that it's easy for a theorist to stand up in front of a room and say that, when in fact the reason they're doing so well is the blood, sweat, and tears of the people who are doing this work in the audience. So I'm not only grateful to you, but I also feel your pain. The question, though, is whether one wants to try to organize this work in such a way that one can construct a kind of a strategy that will take us from the wonderful situation we're in today to a moment when we will actually be able to image and take spectra of an Earth-sized body at 1 astronomical unit from a star like the Sun. That is, at least for some people, but not for everyone, the Holy Grail. So in 2007, the National Science Foundation and NASA commissioned from a committee in the US, the Astronomy and Astrophysics Advisory Committee, a study which was done by a task force called the Exoplanet Task Force to look at how one might get from that moment in time to within 15 years, the point at which one could actually do a terrestrial planet finder type mission with a reasonable chance of success, or at least be able to decide whether such a mission would have a reasonable chance of success. I chaired this committee. There are at least 2 other members of this committee here in the audience. Debbie, are you here today? Deborah Fisher is a member. Hi, how are you? Okay. Jim Casting is a member. Anyone else was a member? No? Okay, good. Anyway, it was a great committee. It's good because if I had forgotten them, I'd be in real trouble. It was a fun time. Deborah actually hosted one of the meetings at San Francisco State, and it was a great committee. What we came up with, in short, was first of all quite logical, and second of all basically ignored, but I'm going to tell you about it anyway. We adopted the approach that for M dwarfs versus FG and K dwarfs, the situation is sufficiently different in terms of detectability that one really wanted to have 2 different tracks, 2 different kinds of strategies. The M dwarfs being smaller, being less massive, a planet of a given mass or a given size will have a larger effect on that planet through radial velocity, astrometry, transits. But at the same time, things that work really well on FG and K dwarfs, like radial velocity in the optical, Doppler spectroscopy in the optical, don't work quite as well on M dwarfs because they're red, they're dim, and they're full of molecules in their atmospheres. So they're really kind of a different beast. So the M dwarfs, it turns out, are objects for which we thought we could identify a kind of a fast track. These are epochs, 1 to 5 years, 5 to 10, and then 10 to 15 to the end of the strategy. You could adopt what one would call a fast track, where you actually are able to use ground-based and existing or planned space assets to potentially get to the point where in the middle of our strategy period, you might actually be getting, through a transit of a quasi-Earth-sized body, probably twice the size of the Earth, around an M-dwarf, a spectrum which might reveal the presence of, for example, water or carbon dioxide, thanks to James Webb Space Telescope, which at least at the time was going to launch in 2013. At the bottom, the FG and K dwarfs are objects for which, if you want to be able to detect an Earth-sized planet around one of these, you really need new technologies. You need new systems in space. But you've got to do a number of things between the present day and when those assets will be ready to even fly something like that, or decide whether you want to fly something like that. So we came up with a number of different scenarios, and I'm just going to show you one. The scenarios were classified according to the frequency of Earth-sized planets roughly in the habitable zone, that's Eta sub-Earth, and the frequency of planets which had exozodies, or the typical exozody level, the typical emission level from dust, or scattering level from dust, for planets in the solar neighborhood, for stars in the solar neighborhood. So it was generally thought that if the typical emission were less than 10 zodies, it would be possible for the projected space-based imaging capabilities, even with a coronagraph, a 4-meter telescope containing a coronagraph in space, to overcome this level of dust emission. So greater than 10 zodies was bad, less than 10 zodies was good. I realize that's an oversimplification, but until we actually do a survey, that's the best one can do. So we assume that in this particular scenario, and that the frequency of occurrence of these Earth-sized planets, sort of roughly in or near the habitable zone, was something like a tenth, 1 out of 10 stars, which is about the occurrence of giant planets around main sequence sun-like stars. And the M-dwarf survey is actually independent of these assumptions. In every one of our scenarios, you pretty much saw the same progression here from, this should be Spitzer, from radial velocity and transit surveys plus Spitzer to James Webb Space Telescope, assuming that the radial velocity and transit surveys, by the time James Webb was launched, would be able to identify some candidate M-dwarf systems which had planets that transit, and that those planets would be close to the size of the Earth, within a factor of 2 or 3. Of course, now we have a lot more time to do those surveys, which is not necessarily a good thing, because James Webb has been delayed for quite a long time. So in fact, Webb may actually be out here, but anyway, that's the way things stand. For the FG and K dwarfs, it was deemed crucial to have radial velocity, aggressive radial velocity studies being done at the same time that Corot and Kepler would do the transit surveys from space. This was after Corot was launched, but before Kepler was launched. And of course now these systems are providing us very quickly with values for Eta sub-Earth, at least for orbits at the inner edge of the habitable zone and inward. In the middle time frame, after some aggressive technology development and exozodiacal surveys to find out whether this is in fact a good number, you would then launch a space astrometry mission like SIM. And I'm going to explain why you want to do that in a minute. And then possibly within the Discovery program or CHEAP program, you complete the statistical survey for orbits between 1 and 10 astronomical units by doing a space-based microlensing mission, which should really clean up on that part of parameter space. And then the pièce de résistance, you actually launch this direct imaging mission. You know where these stars are, and you take spectra of them. So why do we want to obtain the masses of these planets before we go for the Holy Grail and get a spectrum of an Earth? Well, there are two reasons. The first reason is that if Eta sub Earth were to turn out to be 1, you wouldn't need a space-based astrometry mission to find out where these planets are. You just launch the coronagraphic telescope, point it at Alpha Centauri, and get the spectrum of that Earth. But if Eta sub Earth is 0.1 or 0.01, you've got to go begin looking for these objects unless you have a precursor mission that's already found them for you. If you want to waste valuable time with a coronagraphic telescope or an external occulter or whatever, looking at stars and trying to see if you see a little dot next to the star and then go back and take spectra, that's fine. But our view was, based on how the SIM mission was supposed to work, that that was a waste of time. And you launch the SIM mission, you do an astrometric survey, and you identify planets that are the mass of the Earth and the stars that they're orbiting around, and you get their addresses. The second reason for getting the mass is that mass tells you something important about these planets. It tells you the number of protons and neutrons that are in the planet, of course, but it's even more interesting that it tells you something about the materials that are present. So here's a list of densities in grams per cubic centimeter for some of these the objects in our own solar system. Ice, of course, is around 1. Silicates vary from 2 to 4 grams per cc, and metals, represented by iron, are 7 to 8 grams per cc. So here are the rocky terrestrial planets: Mercury, Venus, Earth, Jupiter and Saturn, the moon, our moon, or Europa, and then typical ranges for icy moons between 1 and 2. Now, you can immediately classify objects as kind of terrestrial and outer planet. There are some subtleties here, though. It's not enough to know the density. You also have to know the total mass of the planet, because the total mass tells you what the internal pressures are, and the internal pressures, in turn, tell you how much these materials are being compressed. So Mercury has a relatively high density, even though it's quite a bit smaller than Venus or the Earth. And that means that Mercury must have a much larger fraction of iron in its interior than either Venus or the Earth do. Likewise, we have Jupiter, which at 1 gram per cubic centimeter looks like an icy moon, but we know that it's simply heavily compressed hydrogen and helium because it's 300 times the mass of the Earth. So you need absolute mass and the radius to get the density, and with the mass and the density, or the mass and the radius, you can work out some basic things about the compositions and the properties of these objects. In the giant planet regime, it's particularly interesting because for self-gravitating hydrogen-helium bodies, for low-mass objects, which are generally in the ideal regime, the radius, as the radius increases, the mass increases, or put another way, as you raise the mass, as you add material, the object gets bigger. But hydrogen and helium that's relatively cold, that doesn't have fusion going on in its interior, will begin to become degenerate at masses that are comparable to that of Saturn. And degenerate hydrogen, in particular, it's sometimes called metallic hydrogen, behaves in a very different way. It behaves as a gas of fermions, and as you add more mass to this, rather than expanding, it actually contracts. The compressibility is very large, even though the momentum of the particles is high because of the properties, the behavior of a fermionic gas. And this was recognized by Zapolsky and Salpeter in the 1960s, who plotted radius versus mass, this is flipped the other way around, for cold hydrogen-helium objects, and concluded that Jupiter was essentially near the peak or at the peak for bodies that had solar composition, 75% by mass hydrogen and 25% by mass helium. So this is a pure hydrogen curve, pure helium, pure carbon, magnesium, iron, etc. Now, this would seem to lead to a kind of a degeneracy in the mass and radius. That is, for a given radius, you could have two different mass objects. That turns out not to be the case, of course, because that calculation was done for very cold objects. And as you add mass, you also add thermal energy. And so, in fact, on a plot now that covers a much wider range here, radius versus mass, This is radius in centimeters, mass in terms of solar masses. You can see that objects actually continue to increase in radius because of thermal expansion, because of thermal effects, but not dramatically until hydrogen fusion begins. So in fact, for a given radius, you can have a wide range of masses running from the mass of Jupiter up to several tens of times the mass of Jupiter. So in the case of the giant planets, you don't just want to measure the radius. Of course you want to measure the mass, and that's what radial velocity does. You want to know whether something is a Jupiter or 10 times the mass of Jupiter. And if you add heavy elements or the object is close into the parent star, that will change the radius for a given mass as well. So in the case of giant planets, we're well aware that knowing both the mass and the radius is essential. For terrestrial-sized bodies, it's important too. Again, there's a big difference between, let's say, Mercury and Titan. Okay? This is a plot now from Swift et al. Showing radius versus mass for different amounts of iron. And this is a plot now showing hydrogen-helium objects, ices, and rock and iron, showing different extrasolar planets. But I think a more dramatic example is that if you only knew the radius of an object from a transit, let's say, you wouldn't know a priori whether you had something that was like Titan or was like Mercury, because they're both the same size, but the masses are very different. Now you could say, well, from the position of the object as semi-major axis, I could tell you whether it's all rocky or icy or so on, and that's true to a certain extent. But there's still things that you will not learn. For example, you will not learn the abundance of iron in the interior. And in particular, for Corot 7b, the accuracy of the known radius and the mass are good enough that within, depending on whether you assume 1, 2, or 3 sigma error bars on a plot of the amount of iron, this is really the amount of iron versus radius, you can constrain the amount of iron in the interior, or if you think it's differentiated, which it probably is, the core mass. You will never know that from the radius alone. And if you don't know how much iron is in this body, you cannot make predictions about tectonics and habitability and volcanism or anything like that. So you have to know the mass. Now, even without astrometry, there are ways to do this. Looking at it in terms of transits and radial velocity, there are two different problems. The radial velocity technique gives you a lower limit to the mass, the actual mass, unless transits are occurring. If transits are occurring, you know the orbit is aligned with the observer, and so m sine I is equal to the physical mass. But if that's not the case, you can sometimes, in a multiple planet system, constrain the mass by looking at the orbits of the planets. And this is not a simulation, this is going to be a cartoon. If you imagine looking at successively larger masses, eventually you get to the point where one of the objects is dynamically unstable and leaves. So for systems where you have a few bodies, you have a kind of an upper limit on the mass based on the dynamics. For transits, you have a similar kind of constraint, which comes from transit timing. And in the case of transit timing, if you have a crowded system like Kepler-11, where you have a number of different planets, and this is the raw data that's plotted, but let me show you the transits themselves. So these are transits for the 6 planets in the system, B through G. This is the typical light curve that you would see. The planets are perturbing each other dynamically. And so in contrast to a single planet around a single star, where you know that the center of the transit is going to occur every orbit period, the same period, the periodicity is going to be exact. If you have multiple planets, they will perturb each other and change the center point of the transit. And so this is the observed minus the calculated midpoint times of the transits for each of these planets. And you can do a mutual solution for this system. It doesn't work for G because it's too far out, and obtain the masses of the planets from a transit experiment, which is, I think, a very elegant and wonderful thing. And this is from the Nature paper by Lissauer. So now you have, for these bodies, both their radius and their mass, and therefore you have their densities, and you can plot them and make various inferences about their composition. And then finally, if you just image a planet, can you just, from the size, say that it's an Earth or something? Well, obviously not. The example of Mercury versus Titan is one example. But when we go to direct detection, as opposed to the transit technique where you actually see the size, in the case of direct detection, you're not resolving the planet, you're measuring its brightness. And there's a classic problem in solar system observations of asteroids, where if you only see the optical brightness, the reflected light from the object, let's say the planet, that goes as the albedo times the radius squared, and you don't know whether it's a small object that's very bright or a big object that's very dark. If you have the infrared emission, that emission goes as 1 minus the albedo times r squared. If you have both, you can divide out the radius and determine the albedo. Well, it's highly unlikely that we're going to be flying both an optical and an infrared terrestrial planet finder both at the same time, or at least in our lifetimes. So, you know, you can make arguments, as Traub did, based on colors, that maybe you can determine whether an object is sort of lunar-like or gas giant-like or Earth-like based on the color and then the brightness. But that is an argument based on only the planets in our solar system, and it's too bad that Shakespeare didn't quite say this, or make Hamlet say this, but he should have had Hamlet say this, because this is really the point, that there are going to be more kinds of planets in the heavens than we can really dream of. And so unless we actually get absolute values for the fundamental physical parameters, we're always going to be wondering what the heck we've been looking at. So with that, I'm going to stop and pick up the story, the sad story of the strategy this afternoon, and then conclude with some previews on James Webb Space Telescope whenever that movie is released by Hollywood. So are there any questions at this point, or objections or comments? Thank you. Jim.
I particularly like your last comment there on using colors to figure out if they're terrestrial planets. If you have an early Earth-type planet with a methane haze on it, then it has a color like an outer planet,
yep.
and
Right.
it's still terrestrial.
Yep, that's a very good point. Absolutely. Good. I can see we have a lot of planetary scientists here, because there's a lot more interest in Titan than extrasolar planets. That's good. Yes?
I have a question. If you said that you need to have a mass of a planet, now is it better for you to have the radius of a planet, or to have a planet that is close from us? In other words, if you had to choose between a transit mission that can give you the radius of the planet, but then a planet that is far because of probability and so on, compared to another mission that gives you the address of a planet close, what would you prefer?
Well, if you're only talking about a single planet in each case, I would go for the address of the planet that's close, because I know that I can then follow up and get, you know, observations of, let's say, its size someday. I assume when you talk about address, you're talking about the astrometry. If you're offering me instead the opportunity to get statistics at large distances of a large number of planets by their radii versus the single close-in one, I would actually go for the statistics. Do that first, and then do the close-in ones. But the way you pose the question, I'd go for the close-in one, the address of the close-in one. There was one more. Take one more. Oh, no, actually, yeah, he did it. Yeah.
Has there been progress made on why a lot of the transiting planets are too big for their mass, the inflated?
Yes. So I didn't, because this was sort of a habitable planet school, I didn't talk about that, even though that's very interesting. The close-in giant planets have very large radii. A number of them do. And in fact, you might say, well, they have large radii because they're close to their parent stars, they get hot, and they inflate. But the problem is that you're not looking at a sort of very outer tenuous atmosphere. What you are looking at is the bulk atmosphere of the planet. So you've got to actually inflate essentially the structure of this giant planet in order to satisfy the observations. And that's actually not easy to do, because you've got to get the solar energy somehow down into the object. And there have been various proposals, downward propagating waves. The most interesting recent one was ohmic dissipation in these planets, actually generated by the effect of the presence of the star and the rotation of the planet. And it seems to work if you have high conductivity regions in these interiors. However you do it, though, you've got to bring the planet in when it's thermally expanded at the beginning. These are not ways to blow these planets up like balloons. They have to have migrated in when they were young, when they were quite hot, and when their radii were quite a bit larger than today. And so I think that's telling us that migration happened early, which makes sense. Okay, should we do the coffee break? Thank you.